All right, let's talk about something physicists love to puzzle over, to the point where it almost feels like a cosmic prank: quantum entanglement. Imagine this. You have two particles. They could be light particles or electrons, and you send them flying off in opposite directions, across a lab table, through a maze of fiber optic cables, or even light years apart. The weird part? No matter how far they go, if you measure one, you instantly know something about the other, as if they're communicating faster than the speed of light. But that can't be true, right? Einstein himself famously called this spooky action at a distance. Yet, it's very real. And the details? They're even weirder. Stick with me on this journey because, by the end of this video, you'll see why quantum entanglement simply refuses to make sense in the ways we're used to thinking, but how it's changing everything we thought we knew about physics. Before we dive any deeper, let's clear up some basics. Quantum mechanics is a branch of physics, the kind that governs the smallest pieces of the universe: atoms, electrons, quarks, photons, the invisible scaffolding of reality. It's like stepping into a surrealist painting where nothing behaves the way it does in the larger everyday world. At this tiny scale, particles don't have definite positions, speeds, or states until you observe them. Instead, they exist in these strange states of superpositions, where they're in multiple possibilities at once. It's as if reality itself doesn't fully commit until you look. Now, quantum entanglement takes this to the next level. Here's how it starts. You create two particles in a special intertwined state. Think of it like spinning two coins at the same time, except they don't land on heads or tails until you stop each one. But when you do, you find something eerie. If the first coin ends up heads, the second always comes up tails. If one spins clockwise, the other spins counterclockwise. Always. No matter how far they've drifted apart. And we're not just talking about a coincidence or signal interference. This is solid experimental data, verified countless times in labs worldwide. One thing people have often wondered is, are they somehow talking to each other? Is there a hidden wire connecting them? Here's where it gets frustrating. Every attempt to find such a hidden mechanism fails. What's more, something called Bell's theorem mathematically proves that no hidden variable theory, local to our spacetime, can explain the phenomenon. It forces us to confront two shocking possibilities. Either information somehow moves faster than light, breaking all the rules of relativity, or, and here's the truly unsettling idea, our concepts of locality and time itself are flawed. You might ask, okay, but how does this all work? The answer? Nobody knows. Not yet. That's part of the magic and the headache. What we do know is entanglement has applications that are pushing the boundaries of what's possible in technology. Quantum encryption, for instance, relies on entanglement to create hack-proof systems, since any attempt to tamper with the entangled particle's states instantly destroys the system's coherence. And quantum computers? They use entanglement to process information in ways classical computers can't dream of, solving problems in seconds that would otherwise take centuries. But let's raise the stakes. There's been a long-standing debate about whether reality is deterministic, that is, if everything can be predictably traced back to cause and effect. Classical physics leans heavily on determinism, but quantum entanglement waves a smug little flag at that idea. Why? Observing one particle seems to instantly determine the outcome of the other, implying that some causes and effects might actually exist outside traditional space and time. Einstein hated this idea. He wanted a tidy universe governed by local realism, the principle that nothing can affect something else faster than light, and everything has definite properties, independent of an observer. He might have been brilliantly wrong. Now let's peel back another layer, diving into decoherence and quantum measurement. How does measurement shuffle these entangled particles into their definite states, synchronized across distances? The easy answer is, we don't know. It's tied to what physicists call wave function collapse, another notoriously fuzzy concept in quantum physics. Some interpretations say particles don't take on real physical states until a conscious observer measures them, while others chalk it up to mere interaction. But that's where pilot wave theory and relative state interpretations like many worlds come crashing into the barroom brawl. Pilot wave suggests there's a hidden, guiding wave determining particle behavior. Many worlds? It says every possible outcome spins off into its own universe. So in another reality, you just took a simultaneous left and right turn. See how wild this gets? Still not confused enough? Let's ramp it up with superdense coding and quantum teleportation. First, no, teleportation doesn't beam people like sci-fi. Instead, it's about sending the quantum state of a particle from point A to B via entanglement. Picture encoding a message in the spin of an electron, where the entanglement acts like an invisible courier guaranteeing that info teleports intact even without physically transferring it. Absolutely sci-fi, except it's experimentally done. Superdense coding pushes it further, squeezing more data into fewer qubits thanks to, once again, quantum entanglement. Here's a sneaky twist. Every time you don't look at these particles, they're still interconnected, just as if they've rehearsed their game beforehand. Except quantum physics crushes that analogy too. Entangled particles don't pre-agree on outcomes. Instead, they seem to share a quantum handshake across spacetime at the moment of measurement, ignoring whether they separated moments ago or galaxies away. Now, advanced physics tells us that entanglement may offer insights into the fabric of spacetime itself. For example, theories like ER-EPR, proposed by Leonard Susskind and Juan Maldacena, suggest a deep link between quantum entanglement and wormholes in spacetime. What if tiny linked particles reveal hidden geometric structures that describe reality's secret connectedness? Here lies physics' bleeding edge, a place where tensor mathematics and quantum fields dance together like surreal whispers of truth. But let's zoom back out. Why should anyone care about quantum entanglement? Beyond the raw curiosity, it tips over dominoes in how we view science. It resigns us, triumphantly or tragically, to a universe where some truths play outside the boundaries of everyday logic. Philosophers and physicists alike are continually sparring over how entanglement tweaks our understanding of causality, free will, and even consciousness itself. Some claim it could underpin emergent phenomena, like life's complexity, shouting endlessly about a cosmic interconnectedness that might be more literal than poetic. Ultimately, quantum entanglement challenges our comfort with certainty. We've measured it, leveraged it, even standardized it into commercial technologies. Yet it eludes being reduced to an intuitive mental model, as if it's science's way of teaching humility while unlocking unparalleled potential. So there it is, a tangled, wondrous phenomenon where particles defy the light-speed barrier, filtering surreal secrets into physics labs worldwide. Now imagine, what if it's not just a weird quirk of quantum mechanics? What if entanglement is central to the universe's blueprint? I'll leave that to your imagination. But if you found this video engaging, if it gave you even a few aha or wait, what moments, let me know in the comments. Hyperfocus is a new channel, and your likes, subs, and interactions genuinely make a difference in helping us grow. Till next time, stay hyper-focused, and may your quantum pair always collapse in your favor.